So Peter is the CEO of Chronicle, and he founded it in 2013, where he saw great demand for low latency Java. During the past 7 years, he's been pivotal in growing the software to become a trusted partner to many global tier one banks and hedge funds, as well as cryptocurrency exchanges and traders. In addition, Chronicle open source software is downloaded over 24 million times per year and is used across multiple industries ranging from payments, biometrics, research, and even gaming consoles by companies such as Apple, HubSpot, and PayPal. Prior to this, Peter had many senior consultancy positions at companies including RBS, Barclays, UBS, and Reuters. He's a Java champion and one of the leading global experts in Java development with the most answers on Stack Overflow. He's driven the use of Java in low latency, opening up the skills and capabilities required to build the most demanding apps. So what I'm going to do is I'll hand you over to Peter now. If you have any questions during the presentation, please post them in the chat or the Q&A, and I'll put them to Peter at the end. Peter.
So today's talk is about designing and building and testing low latency microservices. This is a talk that I gave about a few years ago, but this is an updated version of that talk. And in fact, this is a talk I've been giving in various forms for about nearly 6 years now. So a lot of the techniques we're talking about have matured, but they're not that new from our perspective, but they may be new to many listeners who are not familiar or have never come across situations where we needed to have really low latencies, such as they do in banking and hedge funds. A little bit more about me. I've got gold badges on Stack Overflow in many categories, and in fact, the top 3 there, memory, file I/O, and concurrency. I was the first one to get a gold badge. So it gives you some idea of my bent and interest. This is a self-funded company. We get downloads from 300,000 different IP addresses in a month. The majority of revenue actually comes from tier 1 banks. So some of the use cases for the sort of technology that we're about to talk about are things like a low latency fix engine, where wire to wire, they want to have latencies that are consistently low, say 20 microseconds, or you want replication between machines at a consistently low latency, or on a single machine, you just need very low latency persisted messaging between microservices. And so a lot of what this talk is about is not actually about our product set. It's more about the open source and the design methodology behind it. So you can try out a lot of these things yourself. Event-driven architectures are very common in our industry to handle real-time events as they happen. And by real time, we're talking latencies far less than you can see. So we're talking well under a millisecond, usually measured in tens of microseconds. So they're the sort of latencies that we want to be able to achieve to respond to anything that happens in the market. Event-driven architectures help support that. One of the advantages of having a monolith is that it's very easy to deploy all at once. And so monoliths are good to start with when you're first developing them. But over time, as they mature and as they get bigger and bigger, they can become cumbersome. And so this is where microservices come in to help dissect the functionality and break it up and make each component much more manageable. However, even though we favor microservices in production, it can actually be easier to work with a monolith in development. So one of the things we do is we create either test harnesses or for unit tests or for integration tests, where you actually fire up multiple services that will be separate processes in production, but in testing and debugging, it's all in one process. You can start them all up and shut them all down without having to start up lots and lots of applications. And typically, because all of this is low latency, we're talking about taking a fraction of a second to start up and shut down all of the systems. We're not talking about minutes to start things up. When we look at unit testing this stuff, we want to actually run many unit tests with complete systems starting up and shutting down every second. We're typically looking at about 50 milliseconds to start up a simple test, run the test, check everything, and shut it down again. That allows us to run more tests. Web-based microservices are very useful for interacting with web clients, and this is another capability that you still need to have. It's not really, it can be somewhat event-driven with things like WebSockets, but for the most part, it's often interactive request-response type operations. And then you might subscribe to events as they happen, and they can be event-driven. But a key part of most web microservices is being able to handle requests. One of the things that really shines in terms of event-driven architectures is not just that it's performant, but it can also be made deterministic. Everything that that process knows, everything that the service has access to, is fed to it as an event and in a reproducible order. So that means that the state, that the component then becomes a state machine, and it will reproduce exactly the same state every time at that point. This makes things like failover a lot easier because you can have a secondary machine running the same inputs. It will be in exactly the same state as long as the code is the same, and you can ensure that they're completely in sync, and that makes having multiple way redundancy, hot redundancy, much easier. It can also help a lot in debugging because you can take all of the reproduce it on a test system or on your PC, and you can look at your code and reproduce it because you've got access to all of the data, everything that process knew when it knew it, and you can have confidence you've really fixed that bug, not fixed maybe a bug or something you thought was a problem, but turned out wasn't actually the problem. You can have confidence, you replay the data after fixing it, and you can see that it's now behaving correctly. It can also be extremely useful when you have obscure problems that are hard to reproduce without a sort of a long sequence of events to recreate them. Like they don't just happen from just a small set of inputs. And last but not least, it can be very useful for having realistic warm-ups. So one of the key things in a low latency system is how do you warm up the code? How do you ensure that it's already compiled and hot as soon as you get the first message that you really care about entering the system? And what you can do is you can just replay a canned set of realistic data, real data, not just sort of some sort of fake data. You can run some real data through the system because we can run through more than enough data in a few seconds to trigger all the key code to be warmed up. And so it's just a part of startup. And then when you run the program, it's all the key code is already warmed up with realistic inputs. Another thing that can be is potentially a real-time replacement for what is commonly used at either a database or a durable messaging system. It doesn't provide the same guarantees as those systems, but sometimes databases can get overused as well. So they can be used for things that didn't actually need a database for. It's just that it was there and it did the job, so why not use it? The reason it may be that actually the database is then being overutilized, it's not performing, and there are alternative approaches such as an event-driven microservice that can perform very well, still provide enough guarantees of what you need in terms of durability of your information, and be much easier to deploy and test and debug. So one of my favorite quotes is that perfection is not achieved when there's nothing more to add, but when there's nothing left to take away. One of the key things that I note again and again, the difference between a junior developer and a senior developer is that junior developers often measure their productivity in how many lines of code they deleted, and the program still worked. That is, of course. And so, so one of your key objectives is not how much can you add, how complicated, how difficult to maintain you can make a system, but how easy can you maintain? How simple and elegant can your system be, and still do everything it needs to do? And one of the benefits of this is that if you do less work, there's less accidental complexity, it will also run faster. It will handle higher peak bursts in load. It can become more reliable because it can handle these big bursts and it doesn't cause the system to come down. So it's really about removing accidental complexity. And certainly from my experiences, you'd be surprised how much accidental complexity can be in a system. So I'll show you an example later where two systems are both written in Java, are both doing the same work, they're doing the same operation, yet one of them is 700 times faster than the other. Right, so over 99% of the latency is accidental. It's not required for that particular benchmark at least. And so you can actually reduce latency substantially just by removing things that just don't need to be done. So some of the common sources of latency are they're called business logic. This is generally, you can optimize the business logic, but generally speaking, there's not a huge amount of gains that you can make. You might get a factor of 10, 20, 30%, a factor of 2 or 3, but you often don't get dramatic improvements in business logic without throwing more CPU at them. It's an area that's good to be able to optimize, but often it's not as easy to optimize as some of these other things. So the network and the OS can add significant latency. And sometimes, in some cases, the network and the OS is the biggest piece of latency. And in fact, some of the techniques we use are designed to either avoid the network or the OS. So for example, we can send messages between processes without involving the operating system, without involving any loopback networking or TCP. The processes are talking to each other directly. One of the things that we often advocate is that people put in kernel bypass driver network cards where the drivers are running in user space. And that's another example of where you're just avoiding the operating system to reduce latencies. Certainly, messaging and persistence between processes can be a significant source of latency, but this is one of the areas you can actually make huge gains if that's your bottleneck. If it's not your bottleneck, then actually, you're only going to save, so you can actually make huge gains. Garbage collection is another area where you can make a striking reduction in how much garbage you're producing. And a lot of Java developers are just so used to the garbage collector running all the time and producing a lot of garbage that they just expect it. They often think, well, there's nothing you can do about it because it's just the way it is, right? And maybe we can tune it a bit, but actually, it's a lot easier to tune the garbage collector if you don't create so much garbage, and then it also becomes less important to tune it. But reducing the amount of garbage you create can significantly improve the performance of an application. So it's not just between pauses. It's actually the amount of the running performance of your application between those pauses can also increase by a factor of 2 or 3 just by reducing the amount of garbage you're creating. So just looking at some of the typical systems that we work on. So a typical trading system might handle an average of about 50,000 messages a second. So that's a single threaded process. Obviously, more machines, more processes, you can handle more load. But and this is not peak. This is just what it will sustain. However, you can get significant bursts of maybe 10 times that. Is not unusual, 10 times or more. And so you need to be able to handle very short bursts of maybe 500,000 or more messages in a second. And for example, a non-farm payroll is a very common monthly event that triggers an enormous amount of activity all at once for maybe a few minutes. But that's when you often make or lose the most money. So that's the use case you need to be able to handle. So in extreme cases, we actually have people that want both low latency and very low throughput. So one of the extremes, which is difficult to tune for, is when you've only got 1 or 2 messages a minute. And a lot of the reason that that's challenging is that so much of the system is designed to reduce power. So your system will power down, slow down, and if it sees that you're not doing very much, it will pull back on the power consumption. But then that means that when you do actually need to do something, it's feeling very sleepy, or the caches are cold, and you can get several times higher latency with, say, 1 message a minute as you can with, say, 1 message a second, right? And often 1 message a second is quite a lot worse than 1,000 messages a second, which is a surprising result, that actually lower throughputs, generally really low throughputs, actually result in worse latencies than sort of moderate, continuous traffic. So on the other extreme, we see some use cases where there's a need to handle bursts that are well over 1 million events a second, and that's quite a design challenge in itself. But that's one of the more extreme use cases. So it's sort of typical latencies that we generally see with real business logic. So obviously, if you look at any of our benchmarks, we're quoting lower figures than this, because we're only doing trivial business logic. But in this case, we're looking at more realistic examples where there is business logic, the processes are doing something that is useful for a business case, and then you start to see something that's in the tens of microseconds between reading a message and writing a message. And that's how much does it add, so including serialization, persistence, and so on. In more extreme cases, you might see either, say, 5 or even half a millisecond, 5 microseconds, half a millisecond. But that's sort of more these are sort of use cases we generally see these sort of microservices being useful. And by the way, this is all, we're talking about native Java here. We're talking about standard OpenJDK, JVM. A lot of clients are still on Java 8, although many are moving more towards Java 11, Java 17. But many, this is still with even with Java 8. A sort of typical message size is around 1/4 of a kilobyte. And again, we do see extremes in terms of message sizes. The smallest tends to be about 40 bytes. And in some cases, we see up to multiple megabytes. But certainly when we do our benchmarks, we tend to base it around 1/4 of a kilobyte, because that's a very common use case. This is smaller than a lot of other products. When they benchmark, they might look at more of a bigger messages, but we're kind of working with the assumption that clients will make the messages compact as possible. So we've got lots of options for making messages more compact, but in any case, this is a size that clients actually generally use in reality after they've done all of this. Another key thing which is unusual for low latency microservices is that to get consistent low latencies, you need to have a lot of headroom. So you want to have a system that's designed to be somewhere between 1% and 10% utilized. And the reason for this is when you get a burst of activity, you want to be able to catch up very quickly. So for example, if you're 1% utilized, then 1 in 100 times there will already be a message being processed. So that means that your 99th percentile, your worst 1 in 100, is being doubled by the fact that you have a 1% utilization. So even though 1% utilization sounds really low, already it's doubling your 99th percentile. With 10% utilization, you're doubling your 90th percentile. So 1 in 10 times when a message comes in, the previous message is already being processed. So you, in fact, even 10% utilization will be doubling your 90th percentile, and your 99th percentile will be substantially higher because you're running at 10% utilization. So, so even though these utilizations sound quite low, they will be already having a measurable impact on your latencies, particularly your higher percentiles. This has a different so one of the side effects of this is that you don't necessarily need to scale out rapidly because you're kind of building that in. You're kind of building in the ability to double your load or triple your load or even handle 10 times for short periods of time already. It's already built in to that assumption. So you can go up to 100% for a very short period, and then it should cope with that quite readily and handle it going back down to normal. Part of the reason is these bursts last a very short amount of time, very short time. So even a sizable burst might last only about a few minutes. So like the non-farm payroll example, but a lot of the more common cases, these bursts might last for maybe 10 messages. And so we're talking about something that might only last a few milliseconds as a burst. And so then it's not practical to spin up another service to handle those messages because by the time the service has started, all those messages have been processed. So I'll give an example of, depending on your utilization, how long does it take to drain a burst of activity? So say you've got a system that's running at 50,000 messages a second, and it gets a burst of 2 million messages. How long does it take to drain all that big burst and go back to normal? Well, if you're running at 80% utilization, which is actually more typical of a lot of web servers, that's not certainly not an unusual figure. A big burst, in this case, takes quite a long time to drain. We're looking at several minutes. But if you're only 50% utilized, which is actually not considered particularly high, you're already dropping the amount of time it takes to return to normal to 40 seconds. But if you're only 10% utilized, you can return to normal in about 4.5 seconds. And if you're 1% utilized, it's a fraction of a second to process those 2 million messages. So designing a system to have a low utilization can allow you to handle very large bursts quite gracefully and recover back to normal. And that means that you can also improve your reliability of your system because big bursts are not going to cause it to fall over. You've designed your system to be able to handle them right from the start. Now, you might think, well, is this wasting a lot of hardware? Well, when we're talking about 1 to 10% utilization, we're still only talking about, in most cases, we're talking about still one machine. So maybe the machine's a little bit bigger than it needs to be, but in general, we're just trying to make it more efficient so that one machine can do everything it needs to be done, but still only be 10% utilized when that happens. So typically, an event-driven system, you have events coming in to a service, and it produces events out. And those events out are often passed on to another service. So you've got the orange service on the left. It's receiving events from multiple sources. It's producing a series of events, which in turn is producing a series of events to another one. Finally, those events get passed out via a gateway can be deployed into how we do the testing methodology, or they can be tested collectively. Although that's relatively rare, it's very useful when you have that situation. But very much we focus on these core systems. Now, in the future, we're broadening our appeal to also look at, well, how can we do the gateways efficiently? But for today's talk, and that will be followed up in the subsequent talk to this one. But for today, we're focusing very much on those centralized services that have normalized data and can run as efficiently and deterministically as possible. So one of the things that we do is that we advocate storing all the inputs and outputs to disk, to storage. Now, in the past, that was potentially quite expensive, but it's getting cheaper and cheaper. You can now store 4 terabytes in a very fast NVMe drive. So this is single copy for about £600. Obviously, if you've got a redundant copy, we're talking about £1,200, but it's really not a lot for that's an enormous amount of storage. With 4 terabytes, you can store 16 billion messages if they're quarter kilobyte each. So that's a lot of messages to process in a fairly and then obviously as the data is kept, you can archive the data off. So this is, you only need to store maybe a day or a week or a month worth of data before you start archiving it off, storing it elsewhere, or just deleting it. So a fairly standard start system might only have about 4 to 8 terabytes. That's a typical size for our build servers as well. But it's not a lot of money these days to have even enterprise-grade redundant storage of that capacity. So storing every message that comes in and out of every service isn't necessarily very expensive. But then you've got a complete org log of everything your process did and why it did it in a completely reproducible way. So this is what I was talking about, doing similar work, but both. So Kafka is written in Java. Chronicle Q is also written in Java. However, the latency profile for doing a similar task, which is passing a message via a queue and then passing a message back. So this is in this test, we're sending a message to a service that's going via a queue, and then that service is sending a message back via a queue, and we're just looking at the round trip time. So what sort of end-to-end latencies do we get? Well, in Kafka's case, it's designed to be lower latency than a database, but it's not really designed to be low latency. It's designed to be able to, it does many things, has a lot of functionality, but low latency isn't really its design point. It's more about log aggregation, which is its real sweet spot. And so the sort of latencies that you get in the milliseconds, multiple milliseconds. And for a lot of use cases, multiple milliseconds is fine. So why not use it? But in some cases, you need something faster than that, or something that has a lot more headroom, so that you can handle bursts quite readily. And so you can see at the very bottom there is the chart there for Chronicle Q. And just to, it is slightly confusing, but Chronicle Q in this example is handling 5 times the load of Kafka, because Kafka couldn't handle that message rate. So we're actually handling 5 times the load of what you can see there, but it's achieving low latencies that are about 700 times lower. Now, if we zoom up on the bottom, it looks like this. So this chart zooms up the previous one by a factor of 100. So obviously, Kafka's off the scale at this point. And here I'm comparing 2 products. One's the open source version of Q. The other one's the closed source version of Q. But even the open source version of Q, you can see it produces very good results. Like the 99th percentile for round trip messaging. So this is writing every message gets written twice, once in each direction, and you're getting about tens of microseconds for the 99th percentile. Another comparison is how much garbage is being produced. So in this case, this is a profile not of the server, but of just the client, right? So I'm not profiling the server as well. I'm just looking at, well, what is the client doing? And this is not unusual for a Java application. You see it's producing quite a lot of garbage. One of the things that makes it look worse is that each of those bars is actually 2 seconds worth. So the rate of garbage being produced is half what it says there in terms of per second. So it's actually producing about 6.5 gigabytes a second, about 13 gigabytes every 2 seconds. Not sure why they picked that, but there you go. Every second would have been easier to do in your head. Every one of those spikes down the bottom is a GC. So you can see that it's heavily trying to GC up and down, sword-toothing. But this is not unusual for a Java application. So it's not particularly bad or anything. It's just this is a sort of Java graph and profile that most Java developers are used to seeing. So they just accept it. Two of the things that you'll note is that the byte array at the top is actually from the API that Kafka uses. Every message is passed via a byte array. So it creates a byte array for each message. So the API itself makes that unavoidable. But in fact, the other objects there are to do with the serialization. I've used Jackson as a serializer because that's a fairly standard serializer that's used with Kafka. And you can see that Jackson also is a significant contributor to the amount of garbage being produced in this application. So how does that compare using Chronicle Q with Chronicle Wire, which is the serialization that Chronicle uses? Well, it's a lot cleaner. So this is doing the same work. So the same number of messages per second are being passed in the same manner, and they're still being persisted. Now, one of the things that is a little bit odd at this point is that the profile is a little bit confused. So it shows allocations, but it doesn't show any memory usage, which is a bit odd. So there must be some memory usage of this allocations. But it's down now at a level that's so low, the profiler doesn't quite know what to do with the data. You can also see that there are some allocations going on, nowhere near as much. In the previous case, the top allocation was 142 gigabytes. Here it's only 5 megabytes, but these are actually being created by the profiler itself. And in fact, everything you can see on the screen is actually being produced by the profiler, not the application itself. There is a little bit of object allocation produced, lost in the noise here, even against the profiler itself. But it does show you that you can have a Java application doing useful work, but not just producing huge amounts of garbage. That's not a given. It doesn't have to be that way if that's not helpful to you. So moving on to correctness and determinism. So one of the benefits of event-driven architectures is that you can design a system that is a state machine that's completely reproducible. You get the same result every time you run it. Now, we go a little bit further than a lot of applications that are in this space, is that we actually even make the clock deterministic, so that if you've got a timestamp produced in an output message, it will produce exactly the same timestamp every time because it's fed from an input. So that's probably taking it a bit further than most people would think of, but we can produce deterministic tests even involving that are time sensitive or have timestamps in them. It's okay, just going on to that point, you can make time replayable as well. This makes recovery a lot easier because not only is time every input is completely reproducible, all the reference data, all the static information you start with. So having a redundant system is just a matter of replaying the same inputs in the same order, and you get the same results, as long as the code is the same, of course. And then that allows you to recreate the state at any point, both for testing, but also for redundancy. Another area which we see increasing value is in live updates. So in this case, what you have is two instances of a service that are actually running different versions of code. So they're reading the same inputs, but they're running they're running through different code, and so you can see how they both behave live in production, and then you can cut over at some point when you're happy with the newer version, but you don't have to switch the old version off. If you suddenly become unhappy with your new version, you can switch back to your old version as well. Replayability and being able to reproduce a problem is often the biggest source of delay in solving issues and having the confidence that you've fixed them. So fixing issues can take a long time, but often it's just reproducing them that takes the most time. So having a system that's designed to make everything reproducible from the start means that helps with the development effort, but also the maintenance and support going further. So we're coming now back to behavior-driven development. So behavior-driven development, so you may have come across a product called Cucumber, which is a very good tool for behavior-driven development. You'll see in a moment why we've taken a slightly different approach, because we've made it much more event-driven. But it's a very popular technique, and it, to some degree, solves some of the problems with event-driven architectures by being much more declarative and being able to see precisely what you want a service to do. So here's an example. So we use YAML instead of Gherkin as our language for describing it. So every event is persisted as a YAML message or a binary form of YAML for the performance side, but for testing, it's a YAML message. And so essentially what happens is that those YAML messages get translated into method calls. So for example, the very first message in the top left here, that event literally gets turned into a method call on a method called opening balance, and the first argument of opening balance is deserialized with the contents there. The same thing happens for the input. So the difference between setup and input is that we don't check what the results of the setup are. We're only interested in the input. So setups can be files can be copied across many tests. You're not too fussed about what happens there. You're really focusing on, well, these are the events we actually care about. And then what it does, because it's for each event in, there's a certain number of events out, we record those events and compare them. Now, having this structure actually makes it easier to maintain. And the reason it makes it easier to maintain is that if the output changes for any reason, we can very easily update it. And you'll see why in a second, because we're doing a text comparison. So we expect a certain output, and we compare the output we actually get on a multi-line text basis. And if there is a discrepancy, we can very easily see what the discrepancy is. So even if you've got a very complex series of events and outputs, it's very easy to very quickly say, oh, well, this is the values that are different. Now, they may be different for a good reason, because you've actually changed the behavior. And so fixing this test becomes very easy. You can just take the actual result, overwrite the output of the YAML, and now you've treated it like a regression test where you say, well, now this is now the expected behavior. And in fact, you can do this for hundreds of tests by enabling a mode where it just runs everything as a regression test. And then for checking, you can compare, before you check it in, you can look at all the tests that produce different results and decide, well, is this a valid change to the output? Is this a valid change to the output? But it does allow you to maintain hundreds of tests and do a change that could touch all of them and be practical. So one of the problems with having hundreds of tests is that how do you maintain them? How do you keep them all up to date? If you make a small but significant change to that breaks every test, how easy is it to fix it all? And in general, although with a lot of approaches, it's prohibitive. It's so difficult to fix, it just doesn't happen. You never really pay back that technical debt for a small improvement that requires a lot of work to fix it. Whereas in this case, a small improvement doesn't mean a lot of work, and so it does get fixed. And so things like technical debt, like say you change the name of a field, for example, it's very easy to just go through to find a replace on all the inputs, check all the outputs still produce the right results, and update them all. We're talking about like 15 minutes to do a change that actually touches maybe several hundred tests. And this is something that we've done a number of times over the years. And in fact, you can see this test from 2018. But anyway. So a lot of the reason why we use text-based outputs is because IDEs have built-in support for this multi-line comparison. So that allows you to easily spot the differences in complex data structures. And you can just copy paste the actual result over the expected result if you want to just say, well, yes, I accept these changes, and you can do it as the bulk change as well. So look at another example now. So this is a slightly more complicated example. We inputted a couple of pieces of reference data that's to do with the trading system, some configuration, and then we input an order. So this is to do with a matching engine. You don't get a result from the first order, you only get a result when a trade, at least when there's two orders that match. So another thing you'll see is that we use nanosecond timestamps. That's something we've made standard for a few years now. That gives us a lot of detail and resolution. And we don't imagine that we will need to make timestamps any more detailed than that for some time. And so after we place it in the second order, this triggers a trade. So the top left is the input after the previous setup, and the bottom right is the output that we get. And because it's much more readable, in theory, I mean, one of the things about behavior-driven tests is in theory that you can get business people to write them. In practice, I haven't found that business people are very keen on writing tests. However, they do like being able to read them and to be able to see what the tests are doing at a higher level. And so being readable, at least to the business, is a real value. So in the next talk, I'll be talking about broadening the design of the system from those core microservices that are all completely deterministic, event-driven systems to how you design and develop gateways and have distributed microservices across many machines and how they talk to each other between machines. But that's all from this talk. I can see that there's a number of questions. Andrew, shall we?
Yeah. So first question is, what is your model of effective debugging on microservices, and how do you lay out your log footprints scattered over?
Right. So, so one of the key things about our logging is that we record every message in and out of every service. So that becomes the log. So you would only need to log something if it's more than that. And in general, that's quite rare that we want to log something that isn't, we don't need it to be machine readable, but it's still interesting. So an example of that is when you start a system. So when you start a system, it doesn't have any inputs, but you want to know that it's in a good state. So in general, when our systems start up, they log a few messages to indicate that everything's working correctly. And some of our performance metrics are not written to the queues. They're often just written to a log. But for the most part, nearly everything in and out of every service is logged via a queue because that's how they talk to each other. So there really isn't a need for additional logging over and above that. And even GC logs. So as you saw, GCs are very rare. In extreme cases, we can have systems that don't mine or collect for an entire day. So the GC logs are often quite empty as well. And in fact, they're generally just turned on to find, because they shouldn't be logging. If they are logging GCs, then there's a problem. That's a hint that something's gone wrong. So it's not that we ignore them, but certainly we don't expect them to be recording much. Now, in terms of debugging them, I go back to my point about combining them. So treating them more as a monolith. So debugging multiple microservices across processes can be quite painful. Trying to trace what's going on when for an issue that you can't just create a unit test for. So obviously, if you can create a unit test for it and you can test one microservice standalone, that's what you should do. However, it's not always that easy. Sometimes you've got issues that only occur when you're running multiple microservices together and you don't really understand the cause. You don't really know, like if you knew which microservice was causing the problem, you could write a unit test for it, but maybe you don't have enough information to do that. So it a whole lot of service. A monolith in multiple threads in a single process, or they can be run as a single thread across. You can have multiple microservices running in the same thread, which makes it even easier to debug. If there's some sort of technique for doing that, that can help make for rapid deployment and testing, but with the understanding that you still need it to be able to be deployed separately when you go into UAT or production. But in the early stages of development, a monolith can actually be easier to work with. And that's one of the key things that you still want to be able to do.
How often do you use parallel streams and how do you profile them operation by operation to find the bottlenecks with JMH, Profiler, or your kit?
Yeah, so parallel streams, one of the things you want to do with parallel streams, you want to make use of all of the CPUs available to you. However, once you've reached applications where we use parallel streams, it's usually a very coarse level, top of your data. You may not need it all. So I can think of add 300 lines of code. However, we only used parallel streams in 3 occasions. And that's because those 3 occasions was enough at a high enough level to use every CPU on the machine. And once you've achieved that, there's not really much point breaking up any further. So it's really think about, well, what use it as little as possible. Just sprinkling it all over the place doesn't help, and it may just make things worse. So if you use it as little as possible in just the right places, then you can get a much better result. there was one client I had. They had several hundred threads in their trading system. And they had things like parallel streams, executor services all over the place to parallelize everything. And then what I did was ask them, so what is your throughput and your latency? So if you multiply your throughput by your average latency, so say you've got a throughput of 1,000 a second, and your average latency is a millisecond. You multiply them together, you get your concurrency, how many messages are flowing through your system at any one time. In their case, their concurrency was almost exactly 1. So I suggested, how about you take all of that out? And what they did was they reduced the whole thing down to be single-threaded without even removing synchronized and all the locking they were doing. They reduced it down to a single thread and they sped it up by 10, a factor of 10. So they took it from having several hundred threads down to just one core thread that did most of the work, real work. And they had some supporting threads, but one core thread did most of the work. And they just cut out lots and lots of overhead in the process. And a couple of years after that, they rang me up and said, do you think it might be worth using more than one thread? I said, yes, definitely. Now that you've mastered using one thread, how about use more? But just using lots of threads all over the place doesn't necessarily help. And it certainly makes things a lot more complicated, as you may have alluded to.
When a system goes down, does replay mean replay all the events in the queue from the beginning of time?
Yes, so that is the simplest way of doing it, but that's not always practical. So for a lot of trading systems, it is actually practical because you don't necessarily, you generally have a natural maintenance cycle, either once a day. So say you've got an exchange, an equities exchange, it shuts down for overnight for 8, 12. One of them even shuts down for 18 hours every day. So they only run for 6 hours, and then they're not running for 18. So all you need to do is replay from the start of the day. In FX, you only need to restart from the start of the week, and FX tends to have lower volumes anyway, so that's actually practical. However, a lot of systems you can't just do that. It's not you want something that's much more 24/7. In which case, what you need to do is you need to have continuous snapshotting. So one approach is that you just take a full snapshot, but that adds a lot of latency because potentially you've got a lot of data to snapshot all at once. So what we tend to do is we do a periodic incremental snapshot where we'll do, say, 1% of the data every couple of seconds, or 0.1% of a thousandth of the data every second. If you do a thousandth of the data every second, then your delay for adding that checkpoint is quite small, and you only need to go back about 16 minutes or 20 minutes, say. So if you go back 20 minutes, you can be guaranteed that you will both replay every event in the last 20 minutes, but also recreate the state as well. So then that becomes somewhat more practical. So you can choose it. You can tune how often you snapshot the data, and therefore how far you need to go back to get that to get a full state.
Okay. Is isolating CPU affinity essential, and is there any risks in this technique?
Yes, it can be essential. It depends on the use case. So if you're not looking to get the maximum out of the machine, then isolating CPUs is more trouble than it's worth. If you can get the results you want without CPU utilization, I would just do that. That would be my suggestion. However, certainly if you're trying to maximize what a machine can do, and you want to see how much you can achieve for that, then CPU isolation really does help. And especially if you are looking at the latency profile, what do the high nines look like? Certainly, if you're looking at the 3 and 4 nines, it can make orders of magnitude difference, factor of 10 or more improvement. And certainly when you're at high utilization as well. And in fact, at certain throughputs, you may find that it only works if you've got isolation enabled, that it just doesn't even work if you don't. The system becomes so overloaded it never recovers without it. Now, downsides. Some of the downsides include that you get the best result if you busy wait on an isolated CPU, which may be undesirable depending on the system you're running on. So you may not want to have most of your CPUs at 100% all the time. It doesn't help at all if you've got a virtualized environment, because you don't get a real CPU, so isolating doesn't actually help. It appears to be, it does all the right, it looks like it's doing the right things, but you don't actually get any improvement. Probably the biggest downside is that if you misconfigure it. So if you have two busy waiting threads running assigned to the same CPU, you can get very bad results because it doesn't context switch between them very quickly. It's quite often in seconds between context switching. So both of them will show latencies in the seconds all of a sudden. So that can be quite bad. But if it's correctly configured, or if you use our library, which allocates it for you, so you don't have to configure them yourself, then you can avoid that issue. But in general, I would just say, well, if you can get the results you want without using CPU isolation, I'd probably just stick with that.
Where is it wrong to use event-driven architecture?
Event-driven architecture adds a lot of complexity when if you have to deal with, for example, request response. So user interaction where you press a button and you get a response. It's often a lot simpler just to have that kind of model. It's also, it generally assumes that every event will be handled efficiently. So certainly in our infrastructure, and we've got mechanisms where it will start complaining and telling you what it is your thread is doing if it takes too long. And by too long, we're talking about a few milliseconds. And so it doesn't work quite so well if you're very dependent on, say, a database to perform queries. Adding callbacks and trying to match up reply events against requests can add a lot of complexity to your code if it really isn't needed. So I would look at what is a natural way to interact with a service. And you may find that event-driven is not needed or not desirable for certain use cases. Certainly, any long-running request you will need to make event-driven anyway. So, for example, in a typical exchange, you can put an order in the start of the day and it doesn't get filled till the end of the day. Well, making that a request response doesn't necessarily make a lot of sense. Instead, you want to be able to feed lots of orders in and then be told about what happens to them over the day. There are certain use cases where it's just a lot more natural to design your system that way.
Okay. How do we monitor your queue is not backing up with unprocessed messages?
That's an interesting one, mostly because most queuing systems, they have a notion of back pressure. And in fact, some of the ways you differentiate between different queuing systems is what kind of back pressure do they use? Is it reactive? Is it using a big buffer? Or, at what point does it push back on the producer? Well, one of the key things that we have is because we tend to deal with exchanges, we can't push back on the exchange. It's much more of a fire hose approach. We have to take whatever we get. If we start trying to push back on the exchange, they just cut you off, right? Because they can't slow down to wait for you if you're slow. And so we don't have we don't have directly built in any kind of back pressure between a producer and a consumer. In extreme cases, a producer might be writing data to a queue, and it may be running for quite a few years, not just seconds or minutes or days, but years before a consumer starts up and starts extracting information on what was recorded in that queue. So you can actually have many terabytes, many years between the producer and the consumer. However, that doesn't mean that there aren't situations where you do actually want to track when a consumer is running behind. And in that situation, what we do is we have the option of adding nanosecond timestamps as it passes through a system, and that trace gets longer and longer with each read and write to a queue. So every time it goes through a hop, we add a read timestamp and a write timestamp, and then you can trace like what microservice within the system either took too long to read the message or too long to process the message, and then caused a delay. So we do have mechanisms for doing that, but firstly, that's something that's optional and not everyone uses it. But that's more of a monitoring thing as an afterthought rather than a core part of the way the messaging works.
Last couple, because we're running out of time, or we've run out of time. While using Chronicle Q, are you able to build a last value cache? So a crash process can read the latest value and then read every event. This is different from snapshots, as most messages will have delta updates.
Yes, that is a common use case, and admittedly, the state of things as they are is this tends to be done a bit differently for each use case. So yes, it can be done, but it's not. We would like to improve how we do built-in support for that, and we've got a prototype actually in existence for doing that in a more generic manner. But what most clients do is they just add that in as a microservice themselves. So there's a microservice listening to events and then building up a cache that might go into a Chronicle map or whatever they want to store the data in, and then that gets queried to get latest value. What we are looking to do, as I said, is to have more built-in support for that, but we don't.
Okay. And last question. You mentioned that the system needs to be utilized up to 10%. For the order service, though, surely this is running a hot loop.
Yeah, so 10% utilized is it's not 10% of CPU, it's 10% of what it's capable of. So say a system can do, so it in theory could do 500,000 messages a second. If it's only actually doing 50,000 messages a second, then I'd say that that's 10% utilized. But if it's in a hot loop and you look at it in top, it'll still show up as 100%. It'll always show up as 100%, even if it's doing nothing. So I base utilization based on what you've benchmarked that it's capable of, rather than how much CPU it's actually using.
Right. Well, thank you, Peter. Thank you, everyone, for attending. We've recorded this, so we'll be sending out a link afterwards where you can get access to the recording. That's great. Thank you, Peter.
Thank you. All right.
Thanks a lot.
Thank you, everyone.
Bye. Bye.